Alright, so this is limits and continuity. And in this video, I will be explaining everything you need to know about the topic of limits and continuity. So the first thing we need to understand is what exactly is continuity. And the way I like to think about it is that if you can draw the graph without picking up your pencil, it is continuous. And if I were to formally define that, for all a in the domain of f of x, the limit as x approaches a of f of x equals f of a. And this may seem a little confusing, but hopefully by the end of this video, it'll be clear. So let's do an example. So this example is asking us, is f of x continuous, and it's providing us a graph. So let's look at part A first. So if you look at the graph in part A, it appears that there is a hole in the graph right here, which means that this function is not continuous precisely because there is a whole discontinuity right in the middle of it. And this is what is known as a removable discontinuity, because removable discontinuities are like a hole punched right out of the graph. And now if you look at part B, there are two main things that stand out. First of all, we have a vertical asymptote right here, and that we have a jump right here, which means that part B, the function is not continuous either, because there are two discontinuities in the graph. And this really shows the three main types of discontinuities you will find. You will have removable discontinuities, or holes, like this. You will have infinite discontinuities, or asymptotes, like this. And then you will have non-removable discontinuities, or jumps, like this. Now let's talk about limits. So what are we really talking about when we are talking about a limit? Well, when we were evaluating a limit, we were really just looking at what value does f of x approach as x gets really close to a. And now we need to make a really important distinction. When dealing with limits, we don't care about what actually happens at the point. We only care about what happens as you get really close to the point. So with any limit, the first step should always be to plug in the value. And if you do that, there are three possible scenarios that you will get. Scenario number one, the limit as x approaches a of f of x just gives you a number. If you evaluate the limit and it just gives you a number, you already have your answer, so you're done there. Second scenario, if the limit as x approaches a of f of x gives a number over 0. If you get in this situation, the limit does not exist because a number over 0 is undefined. And then third scenario, if a limit as x approaches a of f of x approaches 0 over 0 or infinity over infinity. These two forms are what is known as indeterminate. And if you get in one of these forms, you need to algebraically rearrange. So let's do an example. So we have the limit as x approaches 2 of x squared, and as always, our first step should always be to plug in the value. So if we do that, we will see that this limit goes to 2 squared, which is equal to 4. Therefore, the limit as x approaches 2 of x squared is equal to 4. However, sometimes it is not so easy. If we look at the next example, the limit as x approaches 2 of x squared minus 4 all over x minus 2. And if we take a look at this, take a closer inspection, we will see that if we plug in 2 for x, this expression goes to 0 over 0, which means that what we need to do is algebraically rearrange this. So if we do that, we will see that this is equal to the limit as x approaches 2 of x plus 2 over x minus 2. This is just the difference of squares rule, all over x minus 2. And we see that the x minus 2 and the x minus 2, they cancel out, leaving us with the limit as x approaches 2 of x plus 2. And now, if you plug in the value of 2 for x, we will see that this gives us an answer of 4. Therefore, the answer to this limit, the limit as x approaches 2 of x squared minus 4 all over x minus 2 is equal to 4. Let's take a look at some other examples. So let's look at the first one. The first one is asking for the limit as x approaches pi over 2 of the secant of x. Well, the secant of x is equivalent to 1 over cosine of x, which means that we can rewrite this limit as the limit as x approaches pi over 2 of 1 over the cosine of x, like that. And now let's try plugging in pi over 2 for x. And if we do that, we see that this limit goes to 1 over the cosine of pi over 2, but the cosine of pi over 2 is the same thing as the cosine of 90 degrees, and the cosine of 90 degrees is 0. So this goes to 1 over 0. We got a number over 0, which means that this limit does not exist. It does not exist. Great. Now let's move on to the second one now. The second one is asking us for the limit as x approaches pi of the tangent of x. So let's plug in pi for x. So that, which means that this goes to the tangent of pi, which is the same as a tangent of 180 degrees, which is 0. So this limit over here is equal to 0. Now let's look at the last one. This last one is a little trickier, but we can still do it. So if we plug in 0 for x, we see that this limit goes to 0 over 0, which means that we're going to have to do some algebraic rearrangement. And in this case, we're going to have to use some trig identities. So this is equal to the limit as x approaches 0 of 1 minus the cosine of x. And we have 2 times sine squared of x. But cosine squared plus sine squared is equal to 1. That's the Pythagorean identity, which means that sine squared of x is equal to 1 minus cosine squared of x. So 2 times 1 minus cosine squared of x, like that, right? And now we can use the difference of square rules to further simplify 1 minus cosine squared of x. So if we do that, we can rewrite all of this as the limit as x approaches 0 of 1 minus cosine of x all over 2 times 1 plus the cosine of x times 1 minus the cosine of x, like that. And now we can see that 1 minus cosine of x and 1 minus cosine of x will cancel out, like that, which means that this leaves us with the limit as x approaches 0 of 1 over 2 times 1 plus the cosine of x, like that. And now we can plug in 0 for x and see what happens. If we do that, we see that this expression over here comes out to 1 over 2 multiplied by 1 plus the cosine of 0 is just 1, right? So 1. So it's 1 divided by 2 times 2, which is 4. So 1 over 4. This is our answer. This limit over here will come out to 1 over 4. All right, let's look at the next example. So we got the limit as x approaches 9 of the square root of x minus 3 all over x minus 9. So if we plug in 9 for x, we see that this expression is going to 0 over 0, which means that we need to algebraically rearrange this limit. So how do we do that? So what we're going to use is that we're going to use conjugates, which meaning that this radical over here, it has a conjugate, which is rad x plus 3. So if we do that, we can actually get rid of the radical and actually make it easier to evaluate. So let's do that. So this is equal to the limit as x approaches 9. And we got rad square root of x minus 3 over x minus 9. We're going to multiply both the numerator and the denominator by the square root of x plus 3. Square root of x plus 3. Like that. And now let's multiply those two things together. So this becomes the limit as x approaches 9. And the square root of x minus 3 multiplied by the square root of x plus 3, we can use the difference of squares rule, the difference of square rule. So if we do that, that is equal to the square root of x squared minus 3 squared, which is x minus 9, all over x minus 9 multiplied by the square root of x plus 3, like that. And we notice that x minus 9 and x minus 9 can cancel each other out, like that. So this leaves us with the limit as x approaches 9 of 1 over the square root of x plus 3. And now let's plug in 9 for x. So if we do that, we see that this limit is going to go to the 1 over the square root of 9 plus 3, which is 1 over 3 plus 3, which is 1 over 6.